couple days ago, I was vibe coding with Claude to create my first custom composer callback. And in this video, I'm going to briefly go over what that process looked like for me. And then I'm going to walk through the final composer callback that I created. Again, using Claude, but still kind of building it up from scratch as much as possible so I could understand it. In between that process, I also did a bit of a detour to go through the Python descriptor guide because that was relevant to the callback that I was writing. And then at the end, I will walk through some of the results of the data type logging that I performed with the callback. So this was a few days ago, wrote up a little TIL blog post, and the first one was pretty much from Claude. I gave it a trainer.py, I gave it a callback example from their documentation, and it pretty much spit this out, and I chucked it in LLM-Foundry's train.py and started logging. So where exactly does this callback go? So if you look at LLM-Foundry /LLM-Foundry /command utils /train.py, on line 558 is where the trainer is defined. And you can see on line 547, here are the callbacks, which is a list. So anywhere above line 558, you can define your callback, append it to the list of callbacks, and it'll get passed into the trainer, and it'll do whatever your functionality is. So my intention for this callback was to log the different data types throughout training, and I wanted to understand what actually goes on during mixed precision. So that's the overall goal that I'm trying to achieve, is logging data types for weights, gradients, activations, loss, optimizer states throughout the training loop, so I can understand, what is this kind of mixed precision going on. So these callbacks for Composer are all based on their event loop, and so it's a event-based kind of callback-based approach, which is built off of FastAI. And everything you see in these brackets are the different events that are available in the callback as event handlers. So here you see fit start, and fit start is right here before the actual training of through the epochs. Here's after backward, here's epoch end, and so on and so forth. So this was the initial version, and what it basically did is that when these events would happen, it would trigger the fit start handler, and then I would call logd types, which basically took the state and the logger and the event name, and it logged a string containing the weight d type for that particular module. So this was, kind of quick and dirty, just to kind of get a sense of how things work. And here you can see the output, and it's logging the data type for the LM head at fit start, which is float 32. Or during the backward pass, qproj LoRa A weights are in float 32. So yeah, that was my kind of first motivation. And then I went back to Claude and we did some more. And I'm not going to go through this one here as much because I'm going to go through my actual callback in a second. So let's look at what the callback actually does. It's a very long piece of code. It's a very long callback. It's probably a couple hundred lines. So I don't know. This doesn't seem efficient. It probably is bloated, but it's also relatively straightforward, except for the before forward event. But going into it, and let me zoom into a little bit. So I'm using modal, and so I have a modal volume called modal checkpoints. And so I'm going to save the log in the dtype tracking folder. The log that's going to be saved starts out as a dictionary with one key, log, and an empty dictionary as its value. And everything is going to go in this empty dictionary. One of the first iterations I did, I had these like nested dictionaries, but when I was doing analysis, there was a lot of unnecessary data processing. So I'm like, let me just chuck everything as a key, and then the value will be the data type. And so I have this one long list of log values, and then I have the data type corresponding to each one. Log interval doesn't really matter because I'm just doing one batch, so I just set it to 1. And then because I'm tracking the activation inputs and outputs, I need to have hooks, and I'm going to use PyTorch's register forward hook. So most of these events, event handlers are straightforward. So here's fit start, and I'm logging the wait type, data type, and then I'm saving the logs. And I do the same thing for epoch start, before data loader, after data loader, batch start. So these kind of initial, from here down to here, everything is pretty straightforward. I'm going to skip before forward for now, because we're going to get to that, because it's going to take the most time. After forward is related. But then before loss, again, pretty straightforward, just logging my weights. After the loss calculation, I'm logging my weights, and I'm logging the loss value data type. And then let's see. Yep, okay. Then we have before backward, I'm just logging weights. After backward, I'm logging gradients, weights, and optimizer states. And then batch end and epoch end, I am logging the weights. And looking at this, I should have called this batch end, but yeah, no worries. At least I have epoch end, so I can capture that. Okay, so those are the event handlers, and we'll get to before, after, forward in a second. Then I have 4 different logging handlers. This one logs wait dtype. So it grabs the model from the composer state. It iterates through the model's named parameters. I remove this prefix so it doesn't clutter up my logs. And then I save the data type for that parameter's weights. And so that's pretty straightforward. I also have the event name. So based on where it was called, before batch or epoch end or, whatever the case may be, it logs the event name. It logs the name of the parameter. And then I end it with :weights so that I can easily pluck out what are my weights data types. Log gradient data types, excuse me. Log gradient data types, or dtypes, is very similar. It goes through my model's named parameters, and if the gradient is not none, then it logs the gradient's data type. And if the gradient is none, it just logs none as the value. And then again, I have this event name, parameter name, :gradients. So again, my first couple iterations, my string structure was kind of all over the place, and it made it very difficult and unnecessarily complicated to analyze the data afterwards. So it took a couple iterations of looking at the final output and trying to analyze it. And then eventually I came to this kind of syntax, or I guess structure for my string. And so you'll see I'm always ending with whatever the entity is. So if it's weights, if it's gradients, if it's loss. And then I'm always starting with event name. And then I'm using a colon as a delimiter, because in some cases the underscore, like before underscore forward, has an underscore. So initially I was using underscore, but then I switched to colon. So that's logging gradients. Logging loss is even simpler. State. The composer state just has a loss value, so you can just grab the dtype. Logging optimizer states, again, I think this is probably a little unnecessarily complicated. It handles like multiple state.optimizers. I'm just using one optimizer, so we could have done without this for loop. But it gets the optimizer state, and then it goes through the items of the opt state value, and then it iterates through the param state, and it stores the optimizer index, the param index, and then whatever the state name is, and then I store that as my event name, this key, and then I end with optimizer state. So I'm always starting with event name, and I'm always ending with optimizer states, so I can do my analysis more easily. And then I have this save logs function that gets called pretty much by every event handler, where I just dump the JSON into the log file, which is called this. So that's the overall structure of my callback. But now let's get into the fun part, which is before forward. So before forward is going to log the activations. And before we get to before forward, I want to go through the composer documentation's description of automatic mixed precision training. Half precision formats can boost model throughput, but not necessarily for free. Very small values can get zeroed out. Small values for the gradient can lead to no weight updates. Very large values can roll over to representations of infinity or not a number. And so this is how they say that it's usually handled. So forward pass and loss are in half precision, except for computations that can cause this overflow issue, and those are done in single precision, so FP32. Backward pass in half precision, store the weights, and perform the optimizer step in single precision, and then convert the model back to half precision. I didn't witness all of these, and so it says it's usually performed as follows, so I'm not as knowledgeable about automatic mixed precision training, so there's some details that I don't quite understand in terms of when it should do what. And they talk about how both single and half precision formats are utilized strategically. So there's this strategy that's involved to kind of avoid some of these pitfalls. So that's what I'm trying to do here, is I'm trying to capture the activation input and the activation output data types. So something that we're going to use is a hook, and the hook is based on the PyTorch register forward hook method. So I have this video, this short TIL video, where I talk about the first time I learned about register forward hook, and in that context I wanted to trace floating point error. So I was trying to get the mean value of outputs and then compare them between two different models to see how changing the floating point precision kind of propagated throughout the model layers. And that's what we're going to see here. So let me show exactly where. So down here, I'm going through all of my layers in my transformer, and then I am appending the call of register forward hook. And register forward hook takes a function that it's going to use, and it exposes to that function the inputs and the outputs and the module that is being hooked. And then it returns, so this register forward hook returns object where you can call object dot remove to remove the hook. So self.hooks is a list, and we're appending to it this object that we can then, in the next, later on, we can iterate through the self hooks and do hook.remove, so that doing cleanup. So that's what register forward hook looks like. The key thing is the hook function, and that's what we have defined ourselves, right? So, and I guess we meaning me and Claude. So here's the hook function. It takes the layer name and the module name, and then it's going to return this hook underscore hook method. And this underscore hook method is what's going to receive the module, the inputs, and the outputs, PyTorch's register forward hook. So underscore hook is the kind of actual workhorse, and then this hook function is a wrapper on it so that it kind of creates this closure so that we can pass the layer name and module name, and that we're going to use for our logging. So in, I want to say all cases, the inputs and outputs at least especially the outputs. I haven't looked at the inputs in detail, but I know that the outputs are usually a tuple. So if the inputs are a tuple and there's greater than 0 inputs, which is not always the case, and we'll talk about why, then I'm just going to directly call my log or access my log. I'm going to add a new key, which is going to be the forward pass, module name, layer name, and then this is the entity that I'm logging, which is the activation input, and it's using the input C type. And I do the same thing for outputs, except here it's if their output is either a tensor or it's going to be a tuple. But the main thing is this line where I'm accessing my dictionary, I'm accessing my log key, and the log key has a value associated of a dictionary, and then I'm adding my key with forward activation output this time, and that is the D type as a string being the value. So in this way, hook function, every time the forward pass is called on this layer in this module, it's going to capture the activation inputs and it's going to capture the activation outputs. So that's cool. However, with the first couple times I did this, I was analyzing the data to kind of understand the kind of data flow and precision flow. I saw that self-attention was not logging its input. And so kind of went on a bit of a rabbit hole that I'm going to briefly talk about. So there was this really helpful GitHub issue in the transformers library where this person had a similar example or issue. They tried to attach a forward hook to the self-attention layer, but it failed. The input was a simple empty token. And yeah, if you look at their hook and they're printing the outputs is just an empty tuple. So why is this? So this awesome answer, which was very helpful, they reference the PyTorch documentation for a register forward hook, and they say the input contains only the positional arguments given to the module. Keyword arguments won't be passed to the hooks and only to the forward. And for self-attention, we can actually go to transformers, and if we look at self-attention, there are no positional arguments. Everything is a keyword argument, right? Hidden states equals hidden states, attention mask equals attention mask, and so on. So what was happening is that PyTorch register forward hook was doing what it intended. It was passing forward to my hook function the positional arguments to the module, of which there are none. And so when I was logging, it was empty. Right? There was nothing there. So it wasn't logging anything for the input because there was nothing in the input. The length of the input tuple was 0. So it wasn't logging. Right? So just to reiterate that point here. Yeah, length of inputs is greater than 0, which it wasn't, so it was never running this function. Or sorry, this call, this line. So what to do? I still wanted to capture the inputs for self-attention. So instead, I monkey patched the forward pass. And monkey patching is another thing that I'm not super used to. So, I had to rely on Claude to kind of get me the first couple drafts, and then I had to do some digging to read the Python documentation, which I'll briefly mention in a second. So how do we monkey patch? Well, we go through each layer, we save the original forward because we want to, once we're done logging, we want to use the original forward so that the data can pass through the model as expected. We save the original forward methods in a dictionary. And then here is the forward patch. So it's a closure to capture the current layer index. So we're going to make patch forward, and that's going to return the patch forward method, which is really the actual forward pass. So what we're going to do is we're going to replace the original forward pass with this forward pass for self-attention. And it's going to take self-attention, it's going to take positional arguments, of which there are none, and it's going to take keyword arguments, which are all of them. So if hidden states is in the keyword arguments, which it's going to be, then it will log the activation input value as the data type of the hidden states. And then once it does that logging, we pass the keyword arguments to the original forward so that our model can function as it's supposed to, and it can, keep moving the data along to the next layer, to the next module. And then we replace the forward method when we use this make patched forward, which is going to return the forward method, and then we call it. You'll notice that there's this get dunder method, and I'm not going to go into it in full detail. I've written up a blog post called Understanding Python Descriptors, which basically walks through the code in the Python documentation's descriptor guide, which is an excellent guide to help understand what descriptors are. But the key thing is, I'm just going to read this here. Functions are descriptors, and descriptors are anything that has a get, set, or delete dunder method. Functions have a get method so that they can be converted to a method when accessed as attributes. The non-data descriptor transforms object.f, given some arguments, call into f object args. Calling class.f becomes f.args, or f given the arguments. So a brief example, so I have this class D, and it has a function f, which just returns self. So I create an instance of D, and if I look at d.f, it is a bound method, right? So this method f is a bound method of D. And bound methods have the function itself, but they also automatically have this self attribute that holds the instance that it's bound to. And what happens here is that if I call this function .get given D, it makes a bound method. And what the benefit of a bound method is which we can see here, is that it automatically passes the object as the first argument, which is self. So if you look at any function or any method, so here's llama decoder layer class, the forward pass, right? The first thing is always self. So there's this dilemma when you are dealing with self-attention, because the first argument has to be self, but self-attention as the forward pass doesn't have any positional arguments. So what was happening was that I was passing self-attention as the first argument to the forward pass of self-attention, and it was reading that as the argument to the hidden states parameter, because that's the first keyword argument. There's no positional arguments. And then I was also passing hidden states after that. So I was doing self, comma, hidden states, comma, attention mask. So it was getting two different values for hidden states. And that was because I was basically trying to use a forward pass, which is a method that's bound to a class or an object. I was trying to use it like a function and not a method. So I had to figure out, how do I kind of absorb this self so that it automatically passes self to my self-attention module. And that's what the get operator or the get method does. So if you have a function and you call get on it and you pass it an object, it'll automatically, when you call that resulting method, when you call it, it'll automatically pass self to it. And so that was exactly what I needed to solve this issue, that self-attention doesn't have positional arguments, so it can't take self as an argument. So I call on the original forward as well as patch forward. So I'm calling it on the patched forward here, and then I'm calling it on the original forward here. Get kind of quote unquote absorbs the self argument, and I'm calling get on the self-attention object, so the self argument is going to be the self-attention object. So then when I actually call the method, I don't have to pass anything except my keyword arguments. So this ensures self-attention is correctly passed as self. And so, yeah, I've written this blog post, but obviously the descriptor guide in the Python docs is, the source of truth. While we're on here, there was this Python discussion forum where this person had the same question that I did. It's not intuitive that dunder get would be used to bind a function to an object, and then we will have a bound method. It's not explicit. What if we changed it to bind? And this was a really great answer because it kind of made me understand what these get, set, and delete methods do for descriptors. If descriptors were only callables that bind as methods when accessed as an attribute, then perhaps bind would be a reasonable name. But the descriptor protocol, meaning something that has a get, set, or a dunder get, dunder set, and dunder delete, is a means of implementing a computed attribute in general, which is not necessarily about binding a callable. So it made me realize that this behavior that when you access get here, the computation, the computed attribute that it's performing is that it's binding this function as a bound method to this object, and bound method's first argument is self, so it's kind of implicitly passing self to it. So that binding to the object and then passing self, that is the quote unquote computation that dunder get does when it's accessed as an attribute on a function. And all functions are descriptors because all functions have a dunder get attribute. So yeah, these couple posts were really helpful. Okay, so at this point, my before forward event handler is complete. I have this monkey patch for self-attention modules. It binds the original forward as well as the patched forward to the self-attention so that when I pass keyword arguments, I don't have to pass self because a bound method already passes self. And the self for a bound method is whatever the method is bound to. So in this case, the method is bound to self-attention. So it's going to pass as self. It's going to pass this self-attention object. So all that's left to do is passing keyword arguments. And that's exactly what I do here. And so what's going to happen is that I now I've monkey patched my self-attention's forward pass so that when I train my model and it passes through the model the keyword arguments that we see here, so it passes hidden states, attention mask, so on, it's first going to run this line. It's going to log the hidden states data type, and then it's going to continue on with the original forward pass, which is the actual self-attention mechanism computation. And that's pretty much it, right? So one key thing to point out is that I can still use a hook for outputs because the outputs are exposed in this hook function. So the hook function exposes module inputs and outputs. The inputs are blank because there's no positional inputs, but the outputs are not blank. So I can still use my hook function and register that on self-attention, and it'll capture the outputs. And then while we are on this topic of forward passes, just to show you what the other forward passes look like, and this is all just copied from the modeling llama.py file in the transformers library. So qproj has the positional argument, just hidden states, no keywords. Gateproj, also positional, no keyword arguments. Upproj, downproj, input layer norm, post-attention layer norm, MLP norm, all of them have positional arguments. None of them have keyword arguments. Only self-attention has keyword arguments. So we don't have to worry about monkey patching all of these. We can just hook with register forward hook, it'll expose the inputs that are positional, and we can do our logging. Okay, so let me just look through this again, but I think that pretty much covers everything that I wanted to in terms of what's in the callback. A couple more things. After forward, we're going to go back, we're going to do some logging. We're going to log the weights. So we're going to go through and we're going to restore the original forward pass. And then we're going to hook.remove so that it, that just basically does some cleanup. I'm not really sure like how critical this is, especially given that I'm just doing one batch, so I only have one forward pass to deal with. So I'm not 100% sure how critical this is, but yeah, I didn't know any better. So, and Claude suggested it, so I used it, and it didn't break anything, at least from what I can tell. All right, so where does this go? Again, if you want to put in, kind of do it the more straightforward way, dump your callback definition in line 554, then do callbacks.append, whatever your callback is. Make sure you do that before the trainer is defined, and then you'll have your callback in the composer trainer. And then here's my modal storage, and here's dtype tracking. And if you look here, then this is what the logs look like. So it's a single dictionary, right? Here's a single dictionary, and the keys are my kind of log strings, and then the values are the data types. And this goes on for, I think it's like 6,000-7,000 lines, and it goes everything from fit start to end of the batch, end of the epoch. So that's what that looks like. Yeah, so let's jump in and let's look at what we actually logged. So I have this parse index function, which I'll get to in a second, but I have posted these logs as gists, and I will be publishing this notebook shortly as a blog post, so you can check that out if you're interested, and if you want to analyze the data, or if you want to see like what the logs look like. And I have this _df function, which is just a data prep type of function. So I have my JSON file. I load the JSON file. I dump it into a data frame. I rename the column from log to dtype. And then my index, which is going to be these guys, these strings, I want to parse that index because that contains all of my different elements of what and where is being logged. And so I'm going to call parse index. So one value of index is a string like this. So fit start :embed tokens.wait :weights, something like that. So what I do is I'm going to prepare structured information in this info dictionary, and I'm going to end up with having the layer number, module, layer name, LoRa layer, training step, and the entity. The entity is the thing of which I'm taking the data type. So I look for layer number, and if there's a match, the order of modules matters. So I had to double check that I understood what was going on by looking at the transformers library. And let me show you real quick. I think I want to go to Llama model. So if we look at the forward pass for Llama model, here we go. So embed tokens is the first thing that gets called. So embed tokens is the first thing. Let's see. And then I think the main thing, I didn't actually do the rotary embeddings, so that could be something I could add. But then it's going to call the decoder layer. So let's look at the decoder layer. And the decoder layer forward pass, input layer norm is the first thing that gets called. So after embed tokens, I have input layer norm. Then I have self-attention. It adds the residual, and then post-attention layer norm, and then MLP. So I have self-attention, post-attention layer norm, MLP. Let's go back. So after self-attention, I have norm, and then I have norm here. And then now in my case, this is a llama for causal LM. So I'm going to look at the forward pass for llama for causal. And here we go. Here's the LM head, is where the hidden states get passed through. So LM head is the last piece. So this is, the data flow as our tokens pass through the model. So I'm going to look for my module, and I think now this is probably old because I think, yeah, I guess it's easier to do that because like in some cases the module is right here, so embed tokens, but in some cases the module is after the layer number, and then there's also the layer name and things like that. So I'm just doing a regex search. I don't know if I say regex or regex. Anyways, so I capture the module, and then I get a 2-digit integer, which is the index of this list that the module's in. So if it was self-attention, it would be 000102, because when I later analyze my data, I wanted to sort it in order. And then I add an underscore, and then I have whatever the actual module name is. So 02 underscore self underscore attention, for example. I do a similar thing for layer name. So I'm checking either the self-attention layers. There's no order that I guess there is an order, but I didn't really think about capturing the order because I don't really go into that depth in this analysis. I check if it's a LoRa layer, so base layer, LoRa A or LoRa B. And if it's not, then I just say not a LoRa layer. And then I have my training steps, and this is the order that you can see in the composer docs for their events. So fit start, epoch start, so on and so forth. And so this is why if you look at my logs, the very first value before the first colon is always the event name. And so that makes it a little easier to just pluck out. So I'm just going to do string split and give me the first value. And then again, I'm doing this ordering index. And then the last thing is always the entity that's being logged. And again, that was a conscious choice. So for example, weights here, or activation input, or gradients, or optimizer states, or activation output, or loss. That's always the last value after the last colon. So I just grab that. Then I return info, which is the dictionary. I pluck out the values in info into these columns, and then I return my data frame. So let's run everything here. So I did two different models. I did model in FP32 and model in BF16. So when you train an LLM-Foundry and you have your YAML file, there's a master weights D-type attribute under the model that you can add. If you in the first case, I did not add the master weights D-type attribute, so it was none. And so by default, it does FP32. In the second YAML that I used, I set master weights D-type to bfloat16 because I wanted to see, what is the difference when you in mixed precision training. All right, so we're going to load our data. And as you can see, I have parsed out all the kind of important pieces. And now I can start analyzing the results. So let's do this. So the first thing I want to look at is what are my LoRa layers in? So this is when we're our FP32 model. If we look at the layers, There's 200 layers that are not using the LoRa, or I guess 210 entities, and then there's a couple thousand. So these are parameter states, gradients, this is everything combined. So for LoRa A and LoRa B and the base layer, all of them are FP32. When you look at BF16, that's an N64. So N64 is our tokens, our input tokens. If we look at BF16, that exists for things that are not a LoRa layer. All right, so now we're going to group by entity. And every entity except for activations are in FP32. So the weights, the optimizer states, the loss, the gradients, some outputs in our activation outputs are FP32, but majority are BF16. Some inputs are BF16, majority are float32. So you can start seeing, where does the mixed precision actually kick in? And I should mention this is a small LM2 135 million parameter model. Okay, so that's cool. And now I can group by training step. And this gives me kind of the same picture, but I think it's a little more clear that as I go from fit start, epoch start, data loader, batch start, the only thing being logged is weights, but that's because there's nothing happening. There's no training happening. Before forward, I have weights. Everything is FP32. And then it's during the forward pass where we actually see any of the mixed precision happening. So it's BF16, BF16. After forward, weights, loss, gradients, optimizer states, everything is in FP32. Or, there's no gradients. So when you look at gradients, you have a bunch of layers that are not, for which we don't have gradients because this is a LoRa trained model. So it's only the LoRa trained gradients that we're looking at. Cool. So that is our FP32. And then let's quickly look at our BF16. Now the story is flipped. All of our LoRa layers, including the base layer, LoRa A and LoRa B, are BF16s. Everything except the loss and some optimizer states are BF16. It was interesting that there are, these 420 optimizer states. I'm curious if, it doesn't really tell you what it's, param 2, param 3, but I didn't really log. I guess it's just the optimizer. So it's not necessarily tied to a specific layer, but I would have to think about that. And then we look at the same data, but we look at it training steps. And again, we see, everything is in BF16 except optimizer states, our loss, and our input tokens, which are integers. And that's it. So yeah, in short, or in summary, it took 3 or 4 iterations with Claude to get to my final composer callback. The final iteration, I did it one event at a time. So Claude and I would write one event handler. I would throw it in the LLM-Foundry code, run the training, see the logs, add another one, run the training, see the logs. So I feel comfortable about what code is being used in the callback. I think where the limitations are the limitations I have about understanding composer, the training loop, the optimizer step. I don't think there's anything too crazy that I'm not getting, but there might be some details, especially around what gets chosen to be FP32 versus what gets chosen to be BF16. It would be interesting to see what is causing that decision. And I would imagine you can kind of do that through logging. Other thing in summary is this idea or this reality that self-attention does not have positional arguments. And so you have to do a monkey patch of the forward pass. Maybe there's another way to do it, but this certainly worked. And I'm grateful because now I understand that functions are descriptors. And when you access the dunder get method as an attribute, it'll bind the function as a method to the object that you pass it so that you can implicitly pass self and then you can pass forward whatever arguments you want to. Super cool. Did not expect to learn that in this process. Definitely appreciate that opportunity to learn Python a bit better. And then, yeah, thanks to Composer and thanks to FastAI, so shout out to Jeremy Howard and team for having this callback approach, because if, initially I wasn't going to do a callback, I was like, okay, maybe I need to go into, fork the Composer repo. Maybe I need to go into the actual trainer.py and put in print statements, or, capture the data types and do some logging there. But it was an order of magnitude, maybe even more, easier just to make this callback, chuck it in the trainer, and now I have, a beautiful set of logs. So as I mentioned, I will be posting this collab as a blog post, and I'll link it at the bottom of the video in the video description below. Please like and subscribe. I'm trying to grow my YouTube channel this year, and so far I've gotten a lot of support, so thank you. And yeah, I will see you in the next video. Take care.